Welcome back. Now in the last video, we'd shown that our amplitude phase form of our general solution is indeed equal to our sine and cosine form. And in doing so, we are able to relate our two sets of undetermined coefficients. We found that A was equal to C times cosine phi, and B was equal to C times sine phi. Now what I want to try and do in this video is let's try and figure out what C and phi are in terms of A and B. That way if you're given one set of undetermined coefficients, you can easily convert to the other set and go back and forth. So let's try and find a way to let's work on C first. So how can we get rid of this phi? Well, I've got an idea. What would happen if we were to take A squared plus B squared? And you may be saying, why would we do that? Well, let's just listen closely and find out. Well, our A term corresponds to C cosine phi. So A squared is C squared cosine squared phi. And we're going to add that with our B squared term, which is just this term squared. It's C squared times sine squared of phi. So now let's just factor out the C squared on both sides. So we're going to get C squared of cosine squared phi plus sine squared phi. Now if you remember your trigonometry, there should be a giant red flag popping out. You should remember that this is one of the most famous trig identities, that sine squared of any angle plus cosine squared of any angle is equal to 1. So we can reduce this whole entire parenthesis equation to 1. Which means that we get C squared is equal to A squared plus B squared, or C is equal to the square root of A squared plus B squared. So, we're able to figure out what C is in terms of A and B. Now let's try and figure out what phi is. So, let's try and figure out a way to get rid of the C terms in these equations. I propose, what if we did B divided by A? Well, that corresponds to C sine phi divided by C cosine phi. And that means that, since these are just multiplied together, that the C terms cancel. And what's sine of an angle divided by cosine of an angle? That's just the tangent of the angle. So now we have B divided by A is equal to tangent of phi. And we want to try and figure out what tangent is. Sorry, what phi is. We want to try and isolate that. So let's invoke what they call inverse trig functions. Basically, if you recall, if you have the inverse tangent or the arctan, and we take the arctan of a tangent of, let's just say, x, that is going to be equal to x. Or other way around, if we have the tangent of an arctan, the inverse tangent of x, that's also going to be equal to x. So if we apply the inverse tangent to both sides, we get that the inverse tangent or arctan of B divided by A is equal to the inverse tangent of the tangent of phi, which is just equal to phi. So we get that our phase phi is equal to the arctan of B divided by A. So now we have equations that can tell us what C and phi are in terms of A and B. Now, I want to show something. I want to show that if we were to plug in these values for C and phi in this equation, that we should hopefully re-get this exact same equation. So let's try and do that out. So we're going to say that with C cosine of omega t minus phi, let's rewrite that. We're going to get square root of A squared plus B squared cosine of parentheses omega t minus our phi term, which is arctan of B divided by A. Now at first guess you may say, okay, that doesn't look anything like this, but let's use the same protocol we used earlier. Let's apply this trigonometric identity of adding angles. So I'm just going to do that right here. I'm going to distribute this messy root term along with it. So let's say that this is our, if this is cosine of a plus b, lowercase a plus b, let's say that this corresponds to one term and this corresponds to the other term. So here we get that this is equal to square root of a squared plus b squared times cosine omega t times cosine of negative arctan of b divided by a minus, now I'm just going to distribute out this root term, so we're going to get minus radical a squared plus b squared times sine omega t times sine of negative arctan of b divided by a. Now you may be thinking, that doesn't help, this just looks like a glorified mess. But it's important to realize that what we did was we just applied the same formula we did earlier. We just applied this same formula, cosine of a plus b is cosine a, cosine b minus sine a, sine b. Now, let's do the next step that we did. Let's simplify it off by using our properties of even and odd functions to get rid of some of these minus signs. So we know that cosine of a negative angle is equal to the cosine of the positive angle. Or let's just say that, keep in mind that this whole arctan function is phi. So cosine of negative phi is equal to cosine phi. So let's just make this positive just to make it all nice and neat. And with the sine term, we know that sine of negative phi is equal to the negative sine of phi. So we can bring that negative outside. And like before, that negative will cancel with this negative. So let's just make these positive and just get rid of that. But we're still left with an unusual task of taking the cosine of an inverse tangent of something. How are we going to do that? Well, it's important to remember that although this inverse tangent thing looks ugly, this is just phi. This was just our phase. Now, we essentially want to try and figure out what cosine of this phase is and what sine of this phase is. Now I propose we invoke one quick rule we used earlier. We said earlier that if you take the tangent of an arctan of some value, you're going to get that value out. So if we're to take the tangent of this arctan of b divided by a, we're going to get b divided by a. And if we think of this arctan as an angle, we can actually just draw it out. So let's think of, this is actually supposed to be a right triangle. Here we go. Let's think of our angle phi. This is equal to the arctan of b divided by a. And we know that the tangent of this angle is b divided by a. But we know from basic trigonometry that the tangent of an angle for, let's say, a right triangle is SOHCAHTOA. It's the opposite divided by the adjacent. So if the opposite divided by the adjacent is equal to b divided by a, let's just label this opposite side b and this adjacent side a. Now we've got a right triangle. We know what two sides are, but we don't know what the hypotenuse is. Let's use Pythagoras' theorem. Essentially, the hypotenuse squared is equal to the square root of this side squared plus this side squared, which means that this hypotenuse is equal to the square root of a squared plus b squared. If you've been paying attention, you recognize that this value is actually c. But let's move on. Now, if we think of this arctan term as an angle phi, and we know what this angle phi is in relation to, let's just say, its opposite side, adjacent side, and hypotenuse, now we can easily figure out what the cosine of this arctan term is. is just the cosine of this angle, which is just cosine that's SOHCAHTOA adjacent divided by hypotenuse. So this means that this whole entire term here is just equal to the adjacent side A divided by the hypotenuse side square root of a squared plus b squared. So let's plug that in. So we get this mess is equal to, let's go back to purple, square root of a squared plus b squared cosine omega t. In this huge term, that is all equal to, as we said, a divided by square root of a squared plus b squared. Now before we go on, you should hopefully notice that this messy root cancels out. Here we have radical a squared plus b squared, and here we have 1 over radical a squared plus b squared. So that cancels out. That made it a lot neater. So let's do the same thing for this sine term. Sine, SOHCAHTOA, that is the opposite divided by the hypotenuse. So sine of this arctan of b divided by a, that is the opposite side, b divided by the hypotenuse, square root of a squared plus b squared. So that means that this whole entire thing is equal to b divided by square root of a squared plus b squared. So let's plug that in. We get square root of a squared plus b squared from right here. Then we get sine omega t. Now this whole mess is equal to, as we said, b divided by square root of a squared plus b squared. And lo and behold, once again, the two radical terms cancel. So what are we left with? We're left with a cosine omega t plus b sine omega t, which is what we want to show. So let's just do a quick recap of what we did. We found out what our c and phi terms are in terms of a and b. Then just to really make sure that these are equal, we plugged in these values here. And then we're left with the task of finding out what what the cosine of that phase was and the sine of that phase was. And from our definition here, we knew that the tangent of that phase was equal to b divided by a. So from that, we're able to construct a nice right triangle, and we're able to find out what the hypotenuse was. So with this right triangle, we're able to figure out what the cosine of that phase was and the sine of what that phase was. And if you notice, they all agree with our earlier definitions here. We can see that since c is equal to the square root of a squared plus b squared, cosine phi is equal to, if we divide by c, we get a divided by square root of a squared plus b squared, and we get doing the same thing here. We get that the sine of phi is equal to b divided by the square root of a squared plus b squared. So that may have been a bit confusing. Hopefully it might have helped. But I'll hopefully see you in the next video.